So I don't know if you've done the area using Riemann sums, but if not, that's okay. I need to turn the volume down because I'm going to show you how to do it. So first of all, we're looking at the sine function from 0 to pi. So the sine function goes like this. It has a maximum height of 1. And then the idea is that we're going to be finding this green area right here. And first, we're going to do it with estimates. And the way to do it with an estimate, that's called a Riemann sum, is we're going to use 10 rectangles. So we take this interval and divide it into tenths. So let me see, that would be the halfway point. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the last one would be at pi. And then the idea is you use a rectangle. So you start this interval right here, and then you start building up a rectangle. And you could use the right endpoint. So I would just take the right endpoint of that, and then I would go up until it hits the function, and then make a rectangle. And the reason for a rectangle is because it's very easy to find the area of a rectangle. It's just the base times the height. So as you can see, this rectangle, as far as this part of the rectangle, that's a very good estimate for the area. But this part would actually be an overestimate. The rectangle is not going to fit perfectly. So then what you could do is say, well, instead of using, let me back up, instead of using the right endpoint, what if I use the midpoint of this interval? So go up until you hit the function and then make a rectangle with that height. And then that rectangle is going to be a decent estimate, but right here, it's going to be missing this area, but it would be counting this area. And those two purple areas are about the same. So that rectangle would be a pretty good approximation. So that's the reason I'm using the midpoint of the rectangle. So then the area of that rectangle, well, the first thing is I need to find out what's the width down here. And that is called delta x. In other words, how much does x change by as you go across the x-axis? Well, delta x, you just subtract the two endpoints and you divide by however many rectangles. So this is A and this is B. Subtract those to find the length of the interval. So pi minus 0, and then divide that into 10 equal pieces. So that's basically what I was doing when I was making these little tick marks right here, is I was going over by pi over 10, although I wasn't being very accurate at that time, but those are all spaced by pi over 10. So that's delta x. So then the area of that rectangle would be the base times the height. So the base is pi over 10. So that's the delta x. And then for the height, well, I got that from using the midpoint. So my picture is getting sort of crowded. So what I'm going to do is just look at the x-axis. The x-axis goes from 0 to pi. And then delta x is pi over 10. So that means this would be pi over 10. And then 2 pi over 10 and 3 pi over 10, et cetera, et cetera. Eventually, when I get to the last one, it's going to be 9 pi over 10. Now, the reason I'm not paying attention to this one is 2 pi over 10, and this one is 3 pi over 10, et cetera, because I'm going to actually plug this into the calculator, and I just need to tell the calculator where to start and where to stop. So I really just need the starting interval and the ending interval, and then I'll tell the calculator to add up all the areas. Okay, since we're using the midpoint, so in between 0 and pi over 10, that's going to be pi over 20. The way that I got that is in the middle, you just add the two numbers together and then divide by 2. So that would be pi over 10 divided by 2, and divided by 2 means times a half. So that gives me the pi over 20. And then for the last endpoint, so you could add them together. So 9 pi over 10 plus pi, and then cut that in half to find the average. So that would be 1/2, let me see, 9 pi over 10 plus 10 pi over 10. So that's 1/2 of 9 plus 10 is 19 pi over 10. And then when you multiply on the bottom, that's going to be 19 pi over 20. So that's this midpoint. Okay, so for the area of that first rectangle, I forgot to finish that one right there. The height would be, take this midpoint right there, which is pi over 10. Oh, sorry, pi over 20. And then you plug that into the sine function. And that right there would be the area of this first rectangle. And then we need to do that 10 times. So plus, and then you go to the next interval right here, et cetera, et cetera. But that's sort of time consuming to do it ourselves. So I'm going to do it on the calculator. So before I switch to the calculator, I'm going to show you what you need to type into the calculator. First of all, you have to tell the calculator sum. So add up the 10 rectangles. Then it has to create a sequence. So that's going to be sequence. So in other words, we have a sequence of 10 rectangles. And then the area formula basically follows this. So it's going to be pi over 10 each time, because each of these intervals has a length of pi over 10. So each rectangle is going to have a base pi over 10. And then tell it the sign. Now what I wanted to do is plug in the pi over 20, and then plug in the next one, and then plug in the next one. So I'll just use a variable x right here. And then on the TI-84, I then need to tell the calculator that I'm using x as a variable. So that's why I need to put comma x. Now tell it where to start. So start at pi over 20. So basically that's going to be this part right here. It's going to plug in pi over 20 to start with. Then tell it where to stop. That's 19 pi over 20, this last interval right here. And the last thing is you just have to tell it how much to go over by each time as it goes from rectangle to rectangle. Well, that right there is delta x. And the delta x is pi over 10. So it's basically always going to be the sum sequence, and then this is the delta x, and then whatever the function is, f of x, tell it X is the variable, where to start, where to stop, and the delta X. So before I go to the calculator, does anybody have any questions? Am I going too fast? Okay, then to the calculator. So as you can see, I was practicing before you got here with a different function. All right. So you see, see where it says stat over by the arrow keys? Well, in yellow, it also says list. So the sum and the sequence are actually list operations. So you have to put second list. Now at the top of the calculator, it says math. So move over or click on math. And then number 5 is the sum. So that's what's going to be doing the adding up of the area of the rectangles. Find the sum. So that just puts it on the screen, and now it's waiting for the rest. So now I need sequence. So go second, list again. And then at the top of the calculator, it says ops for operations. So click on operations. And then number 5 is the sequence. So that's what's going to create the area of the 10 rectangles. Then we need the delta X, which is pi over 10. And then just put sine of X. And then you need to put comma, X is the variable. And then the starting point is pi over 20. The ending point is 19 pi over 20. And the last thing to put is the increment or the delta X, which is pi over 10. Oh, I better double check that my calculator is in radians. Yes, it's in radians. Okay, so it's a 2.008. Does anybody have questions on the calculator part? Okay. So the area, let me make some space right here, was a 2.008. So that is a decent estimate for the area. Now for part B, do the same thing with 100 rectangles. So if it's 100 rectangles, that means that basically this is going to change to be pi over 100 instead of pi over 10. And then we just need to find out where to start, where to stop, and then this will be the delta X pi over 100. So when doing these Riemann sums, I pretty much just draw the whole picture just one time. The rest of the time, I just use the x-axis because that's all I really need to be able to tell the calculator what to do. So the whole interval goes from 0 to pi. Delta x is b minus a over however many rectangles. So that's going to be pi over 100. So that means this first interval is going to go from 0 to pi over 100. Over here, this pi could also be written as 100 pi over 100. So if the delta x is a pi over 100, go to the left by pi over 100, and this will be 99 pi over 100. Then where's the midpoint? So right here, well, that would be half of this pi over 100. So that means that this is pi over 200. And if you compare with that we had pi over 20 before, then it makes sense that this is pi over 200 because we're just adding an extra 0, going from 10 rectangles to 100 rectangles. And then what about this midpoint right here? Well, you could add them together and divide by 2 like I did before, or you could say, well, this is a length of pi over 200. So that means you have to go to the left by pi over 200. So I have, well, I guess I need a common denominator of 200. So I'm going to make that 200 pi over 200. And then go to the left by pi over 200. And then that equals 199 pi over 200. And if you compare that with this one, that sort of makes sense because if the bottom is going to become 200, then instead of a 19, use 199. So to save space, I'm just going to reuse this. So it's going to be the sum sequence, and then the delta x is now pi over 100. And start at pi over 200. Stop at 199 pi over 200. And the delta x is pi over 100. And then go back to the calculator. So I think instead of retyping it, well, usually what I do is I just screen grab it and then I just go and change the numbers. But in case you haven't done this very much, let's just go through the steps again. So you go second list, then go over to math, and number 5 is the sum. And then go second list, go to ops for operations, and number 5 is the sequence. And then it's the delta x, so that's pi over 100 times sine of x, comma, x is the variable, and then start at pi over, what was the first one? It was pi over 200. And then 199 pi over 200. And then finally the delta x, pi over 100. And now, at least to the first 3 decimals, it says the answer is 2.000. So the answer for part B is 2.000. Okay, so now for this one, we're done with the sum sequence. Does anyone have questions on using the calculator with the sum sequence? Yeah. Now there's a couple of ways that we could check our answer. One is you could graph the function. So go to y equals and graph sine of x. And it was from 0 to 2 pi. So I'm going to change the window. Oh, no, it was 0 to pi. I think I said 2 pi, 0 to pi. And if the y values go from 0 to 1, we should be able to see the graph. Yeah, actually, I'm going to zoom out just a little bit. Okay, so then to find the actual area. So you go to calculate. So on the upper left-hand corner, excuse me, at the upper right-hand corner, I'm backwards. On the upper right-hand corner, it says calc. So you go to second calc. And then number 7, which has the integral symbol for finding antiderivatives. Number 7 is how you find area. So you do that. Let me do it on my calculator. And then it'll say lower limit. On this one, it just says lower 0. So you type a 0. And then it says upper limit. And so the upper limit, that's pi. And then hit enter. And it finds the area. And it even shades it for you. So the area is actually 2.000. So our second estimate was actually very good. The area is 2.00. Which to me is amazing because the sine function, like you go places on the sine function and it's always these crazy decimals, 2.329, et cetera, and we're finding the area from 0 to pi, and pi is an irrational number, and yet it turns out the area is exactly 2. Amazing. So this estimate right here was pretty good. Now there's another way to check your answer, which is actually part C and part D, one of the most important ideas in calculus. So find the antiderivative of that sine function. So one way to say antiderivative, or with a symbol, is you put that integral symbol of sine x and then put dx. And notice that this right here is saying sine times dx. Well, look at what this is saying right here. It's saying sine times delta x. It's saying the same thing. So sine times the width, delta x, and then this is really just a big S for sum. So it's really saying the same thing as this. Find the sum when it's sine times the delta x. But instead of using rectangles and instead of using the calculator, we'll use the antiderivative. Does anybody know the antiderivative of sine? I'm not even hearing crickets.
Negative cosine?
That is true. Because when you take the derivative of cosine, it's actually negative sine. So to get rid of that negative, you just put that the answer is negative cosine. Now, usually you put a plus c, but if you have numbers to plug in, you don't need a plus c. So for example, the area is not 2 plus c, it's just 2. So we don't need the plus c. So that's going to be what's called the capital F, or the antiderivative. Okay, then for part D. So take that function and plug in pi and plug in 0, which are the 2 endpoints. So that would be negative cosine of pi minus negative cosine of 0. So let's see, the cosine function looks like this. And when you plug in pi, that's going to be down here. So that's equal to negative 1. So this is going to be negative 1. Oh, wait, it's going to be negative, because there's that other negative right there. It's going to be negative of negative 1. And then these two negatives will become a positive, and cosine of 0 is right here, and that's equal to a 1. So finally, this is going to be a positive 1 plus a positive 1 equals 2. So for the third time in a row, it looks like the area is equal to 2. This part right here is extremely important. In fact, it's so important, it has a name. It's called the fundamental theorem of calculus, or the most important theorem of calculus. Because it's truly amazing that right here, we're just finding the antiderivative. So in other words, what's the opposite of the derivative? And once you've found that negative cosine, it will then tell you what the area is under the sine function. Please hold your applause till the end. Thank you very much. Okay, so now we're going to do the same thing with the square root function. But I switched the order. So we're going to do it using the fundamental theorem of calculus first, and then we're going to do it using 20 rectangles later. So first, find the antiderivative. So in other words, find the antiderivative for the square root of x. Well, the first thing that I would do is rewrite the square root so that it's x to the 1/2. So when you have something like x cubed and you're taking the derivative, so this is just a real quick review of how to find an antiderivative. So to find a derivative, you multiply by 3 and then you subtract 1 from the exponent. So that's going this direction to find the derivative. If you're going the opposite direction to find the antiderivative, then you need to add 1 to its exponent, which will be a 3, and then divide by 3. And once you reduce, that's going to take you back to the original function. So in red, that's what we're going to do right here. Add 1 to the exponent, which is going to be 1/2 or 3/2, and then divide by 3/2. So when you divide by 3/2, you need to invert it. It's going to become 2/3. And then x is to the 3/2. And because we have numbers 0 and 4 to plug in, we're not going to put the plus c. You only put the plus c when you don't have numbers to plug in. Okay, so that is the antiderivative, so that's called capital F. Then plug in the endpoints. So it's going to be 2/3, and then plug in a 4 to the 3/2 power, minus 2/3, and then plug in the 0 to the 3/2 power. Well, the second one, since it's a 0, that's just going to be 0. And for the first one, this means the square root of 4. So the square root of 4 is 2. And after you do that, you could cube it. So it's going to be 2 cubed. So 2/3 times 2 cubed. So 2 cubed is 8. So 2/3 times 8 is going to be 16/3. And usually I would just leave it like that, 16/3. But on part C, we're going to find the decimal answer because we're going to be using the calculator. So this would be 5 1/3. So 5.333, and the 3's go forever. So when we do part C, our answer should be close to that. All right, for part C. So the interval is from 0 to 4, and we're talking about the square root function. So the function is the square root of x on the interval from 0 to 4. And since we're going to be using some sequence on the calculator, I don't really have to draw the whole thing. I just need to look at the interval. So it's going to go from 0 to 4. And then find delta x. So subtract the two numbers, 4 minus 0, and then divide that into 20 equal pieces. So that would be 4 divided by 20. Let's see, that reduces to be 4 divided by 20 is 1/5. I'm going to use the decimal. That's going to be a 0.2. So that means the first interval is going to go from 0 to a 0.2. And then the last interval, well, you have to go to the left by 0.2. So it's going to go from 3.8 to 4. And then use the midpoint. So in the middle of 0 and 0.2 is a 0.1. And for this last interval, the middle of a 3.8 and a 4, that would be a 3.9. So those are the first and the last midpoints. Now you sum the sequence, and then it's the delta x, so that's a 0.2, times the original function, that's the square root of x. So that will give the area of each rectangle. And then tell the calculator that x is the variable. Start at a 0.1 for the first interval. End at 3.9. And then each time we go over by delta x, which is a 0.2. Okay, now moving over to the calculator. So go to second list, and then to math. And number 5 is the sum. And then go to second list, then to ops. And number 5 is the sequence. Let's see, the delta x was 0.2, and then times the square root of x, comma, x is the variable. And then started first one was a 0.1, and the last one was a 3.9. And then delta x is a 0.2. And the actual answer is 5.333. How close is the estimate? As far as the first two decimals, it actually got it right. So the estimate is 5.338. So this turned out to be 5.338. And then calculate the percent error. So percent error, so you take the actual number minus the estimate divided by the actual. And then we want it to be positive, so take absolute value. And then that's going to be a decimal. So then to change it to a percent, multiply by 100. Now to be as accurate as possible, I'm going to use the fraction instead of 5.33. So this is the actual. And then this is my estimate. And then I could do the percent error formula, especially if I have some space. So the percent error is going to be, so the actual, I'll use 16/3 minus 5.338, and then put that in absolute value, divide by 16/3, and then times 100. So now going over to the calculator. If you go to math and then to number, the very first one is ABS, which you might think is anti-lock braking system, but it's not, it's absolute value. So absolute value, 16/3. But of course, you don't have to put the absolute value, because if it says a negative, just don't write down the negative, just ignore the negative. Then minus, and I could either type in 5.338 or I could put second, enter. Oh, hold on, I put the wrong one. Got to start over. Math, number, absolute value, 16/3 minus. So down by the negative sign, it says answer. I'm going to put that second answer. So it's going to take my last answer, and instead of 5.338, it's actually going to put 13 decimals. So that will be as accurate as I could be. And then that gets divided by 16/3. And then that'll be a decimal. So then multiply by 100 to change it to a percent. So that is less than 1%. That's even less than 1/10 of a percent. So 0.094%. So by using only 20 rectangles, we get a pretty accurate answer. So before we go on to the next page, does anyone have any questions? Okay, then some more practice with antiderivatives. Well, with that last one, I found the antiderivative by rewriting it. So rewrite the square root as to the 1/2 power. And then use the opposite of the power rule. So you just add 1 to the exponent. That's going to be 3/2. And then divide by 3/2. So now that I've done the antiderivative, then the integral symbol and the dx go away. And when dividing by 3/2, that means I need to invert and multiply. So that's going to be 2/3, 2x plus 4 to the 3/2. And this one does not have any numbers to plug in, so you need to put the plus c. Just like on the quiz, right, Jose? Don't forget the plus c. Okay, now the other good thing with integration or finding antiderivatives is you could always check your answer. Because if this is the correct answer, I could take the derivative of it. And when I take the derivative, I should get the original square root of 2x plus 4 back. So then check it and see if I did it right. So take the derivative of 2/3 2x plus 4 to the 3/2 plus c. Okay, so for the derivative, use the power rule. So the 3/2 goes in front, and then subtract 1 from the exponent. Well, that 3/2 and the 2/3, they're actually going to cancel each other out completely. Then there's going to be the 2x plus 4 And for the exponent, 3/2 minus 1 is 1/2. And the derivative of c is 0. But I'm not quite done taking the derivative, because this one has an inside part. So you have to take the derivative of that because of the chain rule. So that means that the derivative of the inside is a 2. So then it's times 2. Or in other words, I just got the answer 2, the square root of 2x plus 4. And if you look at the original problem, it was supposed to have the square root of 2x plus 4, so that's right. But it was not supposed to have this extra 2. So then I go, whoa, it's a good thing I checked my answer, because I have an extra 2 in the problem and I somehow need to get rid of that. So then I go back to my answer and I go, you know what? I should have divided by 2, because then if I divide by 2, that divided by 2 will always be there until the very end, and then it'll cancel off that 2. So then I have to readjust my answer and say, I need this extra 2 on the bottom. And actually that 2 is going to cancel that 2. So my final answer is 1/3 and then 2x plus 4 to the 3/2 plus c. So with antiderivatives, it's very much like playing chess. If you know the basics in chess, oh, a queen could move whatever direction, any direction. A pawn can mostly just go forward one space. You know, if you had the basics, then you could play somebody a game of chess. But there's a lot of other things that go into chess, and there's billions of different possibilities. Well, the same thing happens with integration. What I just showed you, that's one way to do it. But having to do the problem and then check my answer and then redo the problem because I didn't quite do it right, that, that's like the beginner's chess game. Yeah, you could do that, but there's better ways to do it. So we're going to do the better way now. And I don't know if you've seen U substitution yet, but if not, that's okay. I'll show you right now. Substitution. I don't know, I forgot how to spell. I think it's like that. So U substitution is basically going to take away the guesswork. So you don't have to try it and then check your answer and then readjust your answer. It's basically just going to take care of it for you. So when you do the U substitution, the U should be whatever's on the inside part. Because when I checked my answer, it was the chain rule that I had forgotten about, and that is what messed me up, and I had to do that extra 2 because of the chain rule. Well, the chain rule comes from the derivative of the inside. So the U substitution says, well, let's start right there. If that's going to be your problem, that's going to mess you up in the future, well, let's just address it right now. So you let U equal the inside part, 2x plus 4. So we're basically doing the chain rule part of it right now. Now take the derivative on each side. So on the left side, we're taking the derivative with respect to x, so it's going to be du dx. And on the right side, the derivative is just a 2. And if you notice, when I did the problem and then I checked my answer, I was missing a 2. Well, that's what the du dx is telling me right now. Hey, don't forget about this 2. You need this 2. Now, the next thing is, this part right here says times dx. So I need a times dx. So what I'll do is just multiply both sides by dx. and then they cancel. Now, if you compare what I have, so right now I have a 2 times dx, and the original problem does not have 2 times dx, it only has dx. So I actually need to eliminate this 2 in this equation. Well, that's easy enough. Just multiply both sides by 1/2. So now that this matches what the original problem says, just a dx, we're ready for the u substitution. So it becomes integral and then square root . And then because 2x plus 4 is equal to u, then we have the square root of u. And then to replace dx, well, dx is equal to 1/2 du, so it's going to be 1/2 times du. And that right there is that extra 2 that when I did it the first time, I was missing that 2 on the bottom and I had to go and put it myself. Well, this u substitution is making sure you don't miss it. It's putting it there for us. Okay, the rest of the problem is like the last one. You replace the square root with the 1/2 power. And then you do the opposite of the power rule. So instead of subtracting 1, you add 1 to the exponent, and that's 3/2, and then divide by 3/2. And so then that leaves, well, you have to invert the 3/2, so that's going to be 2/3. There's also the fraction 1/2, which I'll just put it right here. And then there's u to the 3/2, and then plus c. And then there's only one last step to do, and that is the 2 and this 2 are going to cancel each other out, so it leaves 1/3. And then replace u with the 2x plus 4. So 2x plus 4 is to the 3/2, and then plus c, and then that is the final answer. And this idea of u substitution is so important that you will use it for the rest of calculus. The rest of Math 3A, 3B, 3C, any other place you use calculus, you're going to be using the u substitution over and over and over again. Any questions on the u substitution? Okay. Now, what if it's the same problem basically, but then it has this extra x? So again, use u substitution. So let u equal the inside part, 2x plus 4. So letting u equal the inside part, what's inside of the radical, that is always a good place to start. That's not going to be always what u should equal. With the u substitution, sometimes you have to try something and it doesn't work, and then you try something else and it does work. But a good guiding principle is first try that u equals the inside part. And the beginning steps are going to be the same. Du dx equals just a 2. And then multiply both sides by dx. So du equals 2 times dx. And this second step, where you multiply both sides by dx, that step right there is the same each and every time, So quite often I'll just skip it. I'll just go from the first step to the third step. Not when I first start doing it in class, but after a while, this step right here gets sort of old, doing that exact same thing each and every time. So after a while, you could skip it. Okay, now the next thing is you need to compare. Does this one have 2 times dx? No, it does not. So we need to get rid of this 2 so that we have just dx. And when you're on this step right here, the only thing you can do is multiply by a constant or divide by a constant. You cannot add or subtract, and you cannot use variables. You can only get rid of numbers by multiplying or dividing. So I'm going to multiply both sides by 1/2. Okay, now if you look at the original problem, I know what dx is equal to, so I could replace that dx right there with 1/2 du. And I know what 2x plus 4 is equal to, that's u, so I know what I could put right there. So the green can replace the green and the red could replace the red. But on this one, it then has an extra x, and I have to figure out what to put for x. Well, that's going to come from this step right here. We're going to need to solve for x. So I could subtract 4 from both sides. So u minus 4 equals 2x. And then divide both sides by 2. So u minus 4 divided by 2, that is what x equals. So now I have all of the pieces. So now I could do the actual u substitution. So first of all, in place of that single x, put u minus 4 over 2. And then for the square root part, that's going to be the square root of just u. And then finally, in place of the dx, put 1/2 du. And then we only have a couple more steps. One thing I would do is you can factor out numbers when you're doing integrals. So if you put the 1/2, if you put these two together, that makes a 1/4. And then I could factor out that 1/4. That way I just sort of like move the fractions to the side so they don't confuse me. And then go ahead and distribute. So a u times a u to the 1/2. So a u times a square root. Ooh, that was a crazy square root. So a u times a square root of u means a u to the 1 times a u to the 1/2. And then add the exponent, so that's u to the 3/2. So that's not the integral, that's just algebra. So that's u to the 3/2. And then distribute the u to the -4. So minus 4 square root of u, and I'm going to rewrite the square root as u to the 1/2. Okay, we've done the hard part. Now for the easy part. So add 1 to the exponent. Well, 3/2 plus 1 is 5/2, so then divide by 5/2. And then go to the next one. Add 1 to the exponent is 3/2, so divide by 3/2. So the 1/4 is still factored out. And then for dividing by 5/2, invert that, so it's going to be 2/5 u to the 5/2 minus 4, and then invert the 3/2, so that'll be 2/3, and then u to the 3/2, and then plus a c. So then the last thing to do is replace the u, because u is equal to a 2x plus 4. So it'll be 2/5, and then 2x plus 4 is to the 5/2 power, then minus 8/3, and 2x plus 4 is to the 3/2, and then plus a c at the end. And that is the final answer. If you wanted to, you could distribute the 1/4, but you don't really have to. You could if you want. Okay, so then there's 2 more. Well, I'm going to keep going. Even though it's 11:59, I'm going to keep going. So then what happens is people go, oh, u substitution, that's the answer to every integral. So I'm just going to use u substitution on everything. So u equals, well, which one is the inside function? So the second guiding principle, when it was the square root of 2x plus 4, it was pretty obvious that that was inside the radical. So that's the inside function. Well, with this, what is the inside function? The x is inside of a denominator, but look at this. If you do u equals x, you're basically saying, I'm going to replace the u's with x's, which means you turn the problem into this. And if you compare that with the original, well, that's basically the exact same thing, except you're using the letter u in this instead of the letter x. It didn't make the problem any easier. So the second guiding principle when you're doing the u substitution is the u should equal something more complicated. Because that way, when you take the derivative of it, it's going to make it simpler, and hopefully it'll make our problem simpler. So my next guess would be, how about if u equals the 1 plus x to the 4th? Because that got substituted into the numerator, so maybe that's what I should do. Well, take the derivative of that. And the derivative is going to be 4x cubed. And at that point, my brain goes, I don't really think that's such a good idea because there's no x cubed in this problem. And if you did that next step where you transfer the dx to the other side, this part right here is saying, okay, you're going to need an x cubed times a dx. Well, yeah, there's a dx, but there's no x cubed in the problem, which means this u substitution is not working. So we need to try something else. And the something else is, when you have a fraction and you're only dividing by one thing, then what you could do is you could divide it into 2 fractions as long as you keep the same denominator. So it's going to be 1 divided by x, and then x to the 4th divided by x. So 1 divided by x, I can't simplify that, but the second one I could simplify, that's just going to be x cubed. Technically, this is supposed to be in parentheses because it's all times dx. So the antiderivative for 1 over x, that is natural log of x. And for this one, just add 1 to the exponent, which will be 4, and divide by 4. So it's going to be plus x to the fourth over 4, and then plus is c, and there's the antiderivative. Okay, then for the last one. So the last one is definitely challenging because you could try the same thing that I did last time. Oh, maybe the u should equal the 1 plus x to the fourth. But I'll tell you it's not going to work because when you take the derivative, it's going to be 4x cubed and then multiply both sides. So that means that the problem has to have an x cubed times a dx, and it doesn't. So that doesn't work. And then here's where knowing all of these derivatives is very helpful. Because if you look at that problem that I just had, and then you look at this one, it says if you have a fraction and on the bottom you have 1 plus x squared, that's coming from the derivative of tangent inverse. So on the bottom, do I have a 1 plus x squared? A ver. Well, at first it doesn't look like it, but I could rewrite this problem as 1 plus something squared. And because this says x to the fourth, well, what got squared is an x squared. So x squared squared is x to the fourth. And then use u substitution and let u equal the inside part. Well, inside of this parentheses squared, there is an x squared. So that's going to be the inside part, x squared. Now take the derivative of that. So du equals, take the derivative of x squared is 2x, then multiply both sides by dx. And then what this is saying is you have to have x times dx in the problem. Well, if you look at that, that's exactly what it has, x times dx. All I need to do is eliminate this 2. So on this step right here, you can multiply by a constant, you could divide by a constant, but that's the only thing you could do. So I'll multiply by the constant 1/2. It will then eliminate the 2, so it leaves x times dx, and that is exactly what the original problem has right there, x times dx. So then it's ready for the u substitution. So on the top of the fraction, it had x times dx, and that gets replaced with 1/2 times du. And then this x squared gets replaced with u, so the bottom is 1 plus u squared. Now to make this look a little bit simpler, what I'm going to do is factor out the 1/2. You can always factor out constants. And then I'm going to move the du to the side and put 1 times du. So that's the same thing as du on top, but I'm just moving the du over a little bit. And then if you look at this part, 1 over 1 plus u squared. And if you look at this part, whoops, that the derivative of tangent inverse is 1 over 1 plus x squared. So that means our antiderivative, going backwards, our antiderivative is tangent inverse. So the 1/2 has to stay there, and then it's going to be tangent inverse, and right now we're using the letter u, plus c. And the last step is replace the u with x squared. So 1/2 tangent inverse, replace the u with x squared, put the plus c, and that's the antiderivative. Well, that's it for today. Does anybody have any questions?
Mr. Perkins, are your recordings just for you and your students to look back afterwards, or do you post them to your portal as well?
So